Okay, now coming to chapter 5, slope and deflection. In this chapter, we will find out expression of maximum slope and deflection for different beams under various loading conditions. This chapter will help us to design the beam on basis of stiffness criteria. Okay, at B, delta B is deflection at point B. At theta B is equal to slope of point B. At this point, slope of point B. And this is deflected shape or elastic curve. Delta A is equal to 0, theta A is equal to 0. Boundary conditions as this is fixed. Vertical displacement of any point from its initial position up to elastic curve is known as deflection points. That means this PV dash. Maximum deflection of beam less than allowable deflection condition to design the beam on basis of stiffness criteria. The shape of elastic curve depends on shape of elastic curve. I think the shape of deflection depends on shape of elastic curve. Type of loading, shape of elastic curve. SF is equal to 0, BM is equal to 0. Shape of elastic curve, straight line. SF is equal to 0, BM is equal to constant, pure bending, arc of a circle. SF not equal to 0, BM not equal to 0, parabola, like equation can be secondary, tertiary, quaternary. Here fixed beam load is applied at B, then delta V, theta V given, delta C is equal to question mark. Uh, Delta B, this is given, theta B is given, delta C is equal to question mark. Theta B small, tan theta B is almost equal to theta B. Tan theta B is equal to C dash by B dash C dash. Theta B is equal to C dash C double dash by BC. C dash C double dash is equal to theta B into BC. That means this delta C is equal to C double dash is equal to C dash plus C dash C double dash. Delta C is equal to delta B plus theta B into BC. Straight beam concept. Like there will be questions which can be solved by using standard formula or by some method that we are going to discuss right now. Finds met Okay, material related to prismatic EI flexural rigidity. Standard formulas fixed beam EI m theta b is equal to ml by A, delta b is equal to ml square by 2 EI. If like if fixed beam, then point load theta b is equal to PL square by 2EI, delta b is equal to PL cube by 3EI. And uniformly distributed load fixed beam, theta b is equal to WL cube by 6EI, delta b is equal to WL power 4 by 8EI. Uniformly varying load theta b is equal to WL cube by 24EI, delta b is equal to WL power 4 by 30EI. Simply supported beam P at center, theta A is equal to theta B is equal to PL square by 16 EA, delta C is equal to PL cube by 48 EA. Uniformly distributed load, the theta A is equal to theta B is equal to WL cube by 24 EA. Delta C is equal to 5 by 384 WL power 4 by EA. This is previous year gate question. Both sides moment m is applied, theta a is equal to theta b is equal to ml by 2a, delta c is equal to ml square by 8a. These are better to be remembered. Everything you can calculate even later by formulas, but these are better to be remembered. A Macaulay method or double integration method. Mx is equal to px. Standard formula can't be derived from this as it doesn't have single bending moment equation. It is suitable for prismatic bar constant A. It is suitable when a single equation of bending moment is valid throughout the length of beam. Method: by bending equation at any section of beam, ei d square y by dx square is equal to m by I is equal to e by r, m is equal to ei into 1 by r is equal to radius of curvature, 1 by r is equal to rho is equal to curvature is equal to d square y by dx square. Ei d square y by dx square is equal to m. On integrating, ei dy by dx is equal to mx plus c. This can be represented by y double dash. This can be represented by y dash dy by dx. Okay, integrate again. E I y is equal to mx square by 2 plus c1x plus c2. C1 c2 can be found out from boundary conditions. E I y EIY double dash is equal to M. Differentiate EIY triple prime is equal to dm by dx is equal to V is equal to shear force. Differentiate again EIY y 4 primes is equal to dV by dx is equal to W rate of loading. Find out slope and deflection of free end of given cantilever beam. Free end mxx is equal to uh, half into x into wx by l into x by 3. Like area will give force and it will be at a distance of x by 3 centroid. Then mx is equal to wx cube by 6l. EIY double prime is equal to wx cube by 6l. EIY prime is equal to wx power 4 by 24l plus c1. Boundary condition at x equal to l, y a prime is equal to 0, and like slope at a is equal to 0, c1 is equal to minus wl cube by 24, eiy prime is equal to wx power 4 by 24l minus wl cube by 24, eiyb prime is equal to 0 minus wl cube by 24. At x equal to 0, y is equal to 0. So okay, yb prime can be found out like this: minus wl cube by 24a. Integrating again, we will get this from wx power 5 by 120l minus wl cube by 24x into plus c2. C2 can be found by at x equal to l, ya is equal to 0. X we are taking from this direction. So ya is equal to 0. C2 is equal to WL cube by L power 4 by 24 minus WL power 4 by 120 is equal to WL power 4 by 30. EIY is equal to WX power 5 by 120L minus WL cube by 24 into X plus WL power 4 by 30. At free end X is equal to 0, YB is equal to WL power 4 by 30A, which is in the table, matching with the table. Rho is equal to 1 by r is equal to like this is question from workbook. Based on above formulas only you can get anything. Okay, modified Macaulay method. This method is applicable to beam where equation of bending moment is not same along length of beam. Equation of bending like p1 p2, like it will be changing from c to d, b to c, and a to b. So equation of bending moment should be written on section which should cross all loads and cut uniformly distributed load if any. And in this case there is no uniformly distributed load, but this section will cut all the loads, all the loads. EIY double prime is equal to RA into X minus write in slash or another bracket form, as these may come into picture or may not come into picture depending on the section where we are taking. Uh, like write equations from here, not from C. E I y double prime, like if we integrate this, E I y double prime is equal to like this. No need of constant, right? Like we are writing constant C1 here. Yeah, E I y is equal to R A x cube by 6 plus C1x plus C2 uh, minus of p1 into x minus a whole cube by 6 minus p2 into x minus b whole cube by 6. Boundary conditions at x equal to 0, y is equal to 0. Only one time at x equal to L, yb is equal to 0. Like here, 1, 2, 3, all three terms should be considered as x equal to L. It will cut all loads, but in first case, only first load, first term will be there. The oblique or slash sign in bending moment equation represents that the remaining terms may or may not be valid. Integration constant should be added in the first term only. Format of integration can be noticed as x minus a is integrated as x minus a whole square by 2 and not as x square by 2 minus ax. While applying the boundary condition or finding slope and deflection, only valid terms should be used. That is 0 less than or equal to x less than or equal to a, then only first term should be used. A less than or equal to x less than or equal to b, then first and second term should be used. B less than or equal to x less than or equal to c, both all these three terms should be used. Special case, there is a moment applied, and then ei y double prime is equal to rax minus p into x minus a plus m into x minus b whole power 0. When moment is there, x minus b whole power 0, ei y prime is equal to ra into x square plus c1 minus p into x minus a whole square by 2 plus m into x minus b whole power 1. A special case, if there is uniform distributed load only up to here and not till the end, then we can apply on top and bottom by balancing. Then we can take x at by crossing the x, extend UDL up to nearest support and subtract the extended part. EIY double prime is equal to RA into x minus b into x minus a minus w into x minus b into x minus b by 2 plus double into x minus c into x minus c by 2. Find the slope at b theta b. Only moment is applied, then m by l will be in direction and m by l will be in this direction. EIY double prime is equal to minus m by l into x plus m into x minus l by 2 whole power 0. EIY prime is equal to minus m by l x square by 2 plus c1 slash plus m into x minus l by 2. EIY is equal to minus m by l x cube by 6 plus c1x plus c2 plus m into x minus l by 2 whole square by 2. This is first term, this is second term. At x equal to 0, y is equal to 0, c2 is equal to 0. At x equal to l, y is equal to 0. 0 is equal to minus ml square by 6 plus c1l plus ml square by 8. C1 is equal to ml by 6 minus ml by 8 is equal to ml by 24. C1 in equation 1, ei y prime is equal to minus m by l x square by 2 plus m by l ml by 24 plus m into x minus l by 2. To find slope at b, y prime is equal to 1 by a minus ml by 24 plus ml by 20, a minus ml by 8 plus ml by 24 is equal to minus ml by 12a. Another method, area movement method or Morse method. It is suitable for prismatic and non-prismatic beams both. It is suitable when it is easy to draw M by EI diagram and easy to find the area and centroid of the diagram. It is suitable to it is easy to find zero slope and zero deflection points, which is also known as reference points. Theorem 1 for slope calculation. By bending equation ei d square y by dx square is equal to m, ei dy by dx into dy by dy by dx is equal to m, ei into d theta by dx is equal to m, as dy by dx is theta. Integral a to b d theta is equal to integral a to b m by ei dx. Theta b, which means theta b minus theta a, is equal to area of m by ei diagram between a and b. Between a and b, theta b minus theta a is equal to this area. Okay. Theorem 2, vertical coordinate taken from a point on elastic curve up to tangent drawn from some other point on same elastic curve is given by moment area of m by ai diagram between same two points about which vertical ordinate is taken, or about a point where deflection is required. Okay, for example, let's see the case. Reference point b, delta c is equal to delta b plus theta b into bc plus or minus delta c by b, plus when slope of elastic curve increases from b to c, negative when slope of elastic curve decreases from b to c. Delta c by b is equal to a x bar. A means area of m by ai diagram. X bar is centroid point from C. Reference point A. Delta C is equal to delta A plus theta A into AC plus delta C by A. And this is 0, this is 0. Delta C is equal to delta C by A. Delta C by A. Mean X bar should be taken from C. Okay. P E I, okay, PL, okay, M by A diagram, PL by A will be like this. Theta B minus theta A is equal to half into L into PL by A. Theta B, yes, theta A is 0, theta B is equal to PL square by 2EI. Theorem 2, delta B is equal to delta B by A is equal to half into L into PL by A area. Then from B, the centroid is 2 from 2L by 3 into 2L by 3, delta B is equal to PL square by 3EI. Properties of parabola. Like if you take a curve like this, and then this is area 1, this is area 2. Combined area 1 area 2 will be of rectangle, which will be of area BH. Only one area A1 is equal to n by n plus 1 into BH, where n is order y is equal to ky x power n is curve. Then a1 is equal to n by n plus 1 bh. If y is equal to kx square, then 2y a1 is equal to 2 by 3 bh. A2 is equal to 1 by 3 bh is equal to 1 by n plus 1 bh when y is equal to kx power n. Xi is equal to x1, means centroid of this first area is equal to 3b by 8 for quadratic is equal to n plus 1 by n plus 2 into b by 2 for nth one. X2, this centroid of area 2 from origin from this axis is 3b by 4 for quadratic is equal to n plus 1 by n plus 2 into b. N plus 1 by n plus 2 into b. Find out one question. Find out slope at A and deflection at C. Slope at A and deflection at C. And M by E diagram will be like this, as W is linear, force will W is linear, as W is constant, force will be linear, then M by A will be quadratic. Okay, at center WL square by 8A, we have already done that. Theorem of length theta a minus theta c is equal to 2 by 3 into L by 2 and WL square by 8A. Theta a is equal to WL cube by 24EI. Theorem 2, reference point A, delta a is equal to 0. Delta c is equal to delta a tends to 0 plus theta a into AC minus delta c by A. Slope of elastic curve decreases is equal to WL cube by 24EI into L by 2 minus WL cube by 24EI into 3 by 8 into L by 2 is equal to 5WL power 4 by 384 EI. 5 WL power 4 by 384 EA. Like they are using above equations. P, it will be linear member A diagram only. PL by 4 EI is the highest one. Theta A minus theta C is equal to half into L by 2 into PL by 4 EI. Theta A is equal to PL square by 16 EI. Theorem 2, delta C is equal to delta A plus theta A into AC minus delta C by A. Delta C is equal to PL square by 16 EI into L by 2 minus PL square by 16 EI into 1 by 3 into L by 2 is equal to PL cube by 48 EA. Delta C is equal to PL square by 16 EA into 2 by 3 into L by 2. Moment area of M by A between A and C taken about A. Taken about A. Here it is taken about A. Okay. By moment area method, we have to calculate only distance. We calculate only this distance. Okay, slope and deflection at free end. Here EA itself is changing. Then graph will be changing, but the method will remain same. A divided into A3 parts. A1, A2, A3. Then theta C minus theta A is equal to A1 plus A2 plus A3. Theorem 2, delta C by A is equal to AX bar is equal to A1 X1 bar plus A2 X2 bar plus A3 X3 bar. We'll get the final one. Strain another method, strain energy method, Castich-Greenhouse theorem. It is suitable for prismatic and non-prismatic beams both, but it is very suitable for cantilever frames. Total strain energy of beam U is equal to U bending plus U shear. Here U shear will if U bending is in range of thousands, then U shear will be in range of 1, so it can be neglected. U is equal to U bending is equal to integral mx square dx by 2 EI, and delta is equal to dou U by dou P. Delta, if it is P is in this direction, then in this direction only we will get delta as dou U by dou P. Uh, if there is no point load, then create a point load at dummy load at end, then apply dou U by dou Q, and finally place Q is equal to 0. Theta B is equal to dou U by dou M. Theta A is equal to dou U by dou M. M dash is equal to 0. Dummy moment. According to this method, a deflection at any point in the direction of load is given by partial differentiation of total strain energy with respect to the concentrated load which is acting at that point. If deflection is required at a point where there is no load, then we have to apply one dummy load at that point in direction of deflection. In this case, the deflection is equal to partial differentiation of total strain energy with respect to that dummy load, and in the final result put that dummy load equal to 0. Find out strain energy of beam. U is equal to UAB plus UVC plus UCD. Since AB and CD are symmetrical, AUAB is equal to UCD. Hence U is equal to 2UAB plus UVC. UAB is MX is equal to P into X till that point. UAB is equal to integral 0 to L Px whole square by 2EA dx is equal to P square L cube by 6EA. And UBC is equal to P into L plus X minus Px. Mx is equal to PL. UVC is equal to integral 0 to 2L integral 0 to 12 PL whole square into dx by M by EA is equal to P square L square by 2A into 2L. Okay, like as X is considered from here. differentiate under integration dou u by dou p is equal to dou by dou p of integral m square dx by 2a like is equal to integral 2 mx dou mx by dou p dx by 2a is equal to delta is equal to integral of mx dou mx by dou p into dx by ea. Similarly, theta is equal to integral mx into dou mx by dou m dA dou mx by dou m dx by ea. Like similarly, similar case, we have to differentiate, take differentiation inside, we will get this result. Find out vertical deflection of point C. Effect of axial load is neglected. BC mx is equal to px 0 to L EA AB like there will be load of P here and P here and P here. Like if we remove this whole thing completely, then we will have P here, P here, then PL. Okay, delta C. To balance this PL, there will be P here and P here. Mx is equal to P into X. Delta C is equal to dou U by dou P is equal to dou UBC by dou P plus dou UAB by dou P. Delta CV is equal to integral 0 to L Px into X dx by A plus integral 0 to L Px into X dx by 2EA. Okay, we'll get it like this. If it is not fixed, then this beam will be P and PL will be here. We can find out for this section also. Find out vertical deflection at point B. Delta B vertical is equal to dou U by dou P is equal to integral m theta dou m theta by dou P into r d theta by EA. M theta is equal to P into r sin theta. Theta 0 to pi by 2. Dx is equal to r do theta. Delta BV we can integrate from 0 to pi by 2 PR sin theta into r sin theta into r d theta by A is dou m by dou P. We can find out horizontal deflection of V. Delta V is equal to dou U by dou theta is equal to, okay, this we wrote before. MV is equal to PR sin theta minus Q into, okay, this dummy load we have to apply Q minus Q into R minus R cos theta. Delta VH is equal to integral 0 to pi by 2 PR into dMB by dQ into R d theta by EA. So at Q is equal to 0, we will get it like this, and then we can get horizontal deflection also. Horizontal deflection, okay. One more method is conjugate beam method. If this is the real beam, this is M by EA diagram of real beam is equal to loading diagram of conjugate beam. SFD of conjugate beam is equal to slope diagram of real beam. BMD of conjugate beam is equal to deflection diagram of real beam. See, follow this sequence. M by EI of real beam is loading diagram of conjugate beam. These two are for conjugate beam, then force 2 times derivative, then it may come to slope diagram. Bending moment diagram is 2 times derivative, stiff friction, okay. Like no need to remember as logic, S, so B, D, we can remember it like that. Okay, rules to construct conjugate beam, real beam, conjugate beam. If it is fixed end, then it will be free end, fixed end. Internal hinge, then it replaced by internal roller replaced by internal hinge. Real beam, conjugate beam. Theta a not equal to 0, delta a equal to 0. VA not equal to 0, MA equal to 0. Fixation theta is equal to 0, delta A equal to 0, theta B not equal to 0, the delta B not equal to 0. For conjugate beam, here it is free, then here it is fixed. Simply supported, it will be same. Vn equal to 0, Ma equal to 0, Vv not equal to 0, Mb not equal to 0. Here roller theta delta theta b not equal to 0, delta b equal to 0. Vb replaced by internal hinge fixed free fixed. Vb not equal to 0, Mb equal to 0. Both sides fixed, both sides free. Okay. Question L find out theta b and delta b. Only moment is applied. M by A diagram is like this box which will be loading diagram of conjugate beam. Means here it is free, here it is fixed. Then conjugate beam M by A loading is applied. Newton per meter. L conjugate beam MB. Real beam theta b is conjugate beam SFB. SFB is equal to RB is equal to M by EI into L. Delta A is equal delta A is BMB is equal to MB is equal to ML by AI into L by 2. Delta B. This is delta B. Okay, like this we can solve easily. Find out theta A, theta B, and delta C. Theta A, theta B, and delta C. This is EA, this is EA, PL by 4, PL by 4 EI. Okay. This is loading diagram of conjugate beam. Supports will be same RARB. Sigma FV is equal to 0. Maybe A infinity here. Okay. Sigma F is equal to RA plus RB is equal to half PL by 4A into L by 2. RA plus RB is equal to PL square by 16A. Sigma MZA is equal to 0. RB into L is equal to PL square by 16A into L by 2 plus 1 by 3 into L by 2. RB is equal to PL square by 24A. RA is equal to PL square by 48A. RB theta A SFA is equal to RA is equal to PL square by 48A. Theta B is SFB is equal to RB is equal to PL square by 24A. Delta C BMC is equal to RA into L by 2 is equal to PL cube by 96A. Another theorem, superposition theorem. According to this theorem, the value of slope and deflection at any point is equal to algebraic summation of slope and deflection at that point due to all individual loads. For example, take this cantilever beam which has uniformly distributed load and concentrated load, which is equivalent to separate these two loads. Consider case of acting these two loads separately. Delta B is equal to WL power 4 by 8EA plus PL cube by 3EI. Consider this case like this, but we only have general formula of this case. So uniformly distributed minus this one, we will get to delta b. Delta b is equal to WL power 4 by 8EA minus WL power 4 by 30EA. This delta c is equal to question mark. This is this is combination of these two, and delta c plus delta c is equal to 5 by 384 WL power 4 by 384EA. We know for this case these two delta c plus delta c, these are similar. We will get both delta c same, so half of this 5 WL power 4 by 384EA. Find out deflection at hinge. P is applied, then subtract these two, P by 2 due to symmetry. Delta B is equal to P by 2 L cube by 3EI. If load is unsymmetric, delta B1 is equal to delta B2 RB P minus RB. RB from this also we will get a PRB is equal to P by 2. The free ends of given cantilever beams will have e They must have same deflection, otherwise roller will move out. Will have equal deflection, but I have unequal slope because this will be in this direction, this will be in this direction. Find out slope, find out the final distance between C and F. C and F. Due to these forces, the C will move in this direction, F will move in this direction. Theta B is equal to ml by 2 EI. F dash is equal to CC dash is equal to theta B into B is equal to PAL by 2 EI into B. C dash F dash is equal to L plus 2 PABL by 2 EI is equal to L into 1 plus PAB by EI. These are workbook questions. By using above methods only, we can solve these questions. This equation like r 2r minus delta and delta 2r minus delta into delta is equal to L by 2. Area arc of circle in pure bending case. Sigma by I is equal to m by I is equal to E by r. 1 by r is equal to rho is equal to 0.04 meter inverse. This is in one question. Delta is equal to L square by 8 r is equal to rho L square by 8. In case of pure bending, deflection at middle is equal to L square by 8 r radius of curvature. Simply supported beam of length L is subjected to linear temperature gradient at temperature T at bottom, uh, and find out deflection at mid of span, which means temperature from 0 degrees to T degrees it is varying linearly, and then there will be tension here, due to which pure bending arc of circle L is equal there L on top, L plus L alpha delta T on bottom. L is equal to R theta, L plus L alpha delta T is equal to R plus D into theta. From dividing these two, we will get R is equal to D by alpha delta T. Delta is equal to L square by 8R is equal to L square by 8 into D by alpha delta T. Delta is equal to L square alpha delta T by 8D. Maxwell reciprocal theorem only for concentrated load and concentrated moments. According to this theorem, ratio of deflection at point 1 to the load applied at point 2 is equal to ratio of deflection at the point 2 to the load applied at point 1. Delta 1 by P2 is equal to delta 2 by P1. Theta 1 by M1, theta 1 by M2 is equal to theta 2 by M1, applicable for concentrated load. If P1 is equal to P2, then delta 1 is equal to delta 2. Limitation: in both the cases identical beams should be used. This theorem is applicable only for concentrated loads and moments, not applicable for distributed loads and moments. Okay. Propped cantilever beam, unknowns is equal to 3, equations is equal to 2. Then we have to use compatibility equation. Theta A is equal to 0, delta A is equal to 0, boundary conditions, delta B is equal to 0, mostly used. Find out distance of point of contraflexure from a fixed point. Delta B is equal to 0, delta B downward is equal to delta B upward. Delta B upward is equal to, because of these separate loads calculate by each load separately, then we will get RB is equal to 7.5 kilonewton. We can get at a distance x where m is equal to 0, we can find out the value of reaction at fixed support. EA is equal to 781250 kilonewton per meter square. Assuming no support at free end, delta B is equal to WL power 4 by 8 EA is equal to 10 mm. Deflection resisted by support is equal to 10 minus 6 is equal to 4 mm. 4 mm. RB into L there will be a reaction generated. RB L cube by 3I is equal to 4 mm. Then for RB is equal to 75 Newton. Okay, 75 kilonewton. Supported fixed support is equal to 500 minus 75 is equal to 425 Newton. Just balancing 100 into 5 minus 75 is equal to 425 kilonewton. Find out reaction. Find out proper reaction. Delta V downward cantilever is equal to delta V downward spring. WL power 4 by 8 EI minus RB L cube by 3 EI is equal to RB by K. Is equal to RB by K. These are we are using some constraints here, that is compatibility equations. Okay, RBM is equal to 2PA, delta V is equal to 2PA into L square by 2AI plus 2PAL into L by L EA is equal to 3PA L square by EI. Delta V is equal to RC into 12 whole cube by 3EI. RC is equal to 9PA by 8L. Okay, fixed beam is horizontal will be balanced. RA, RB, MA, MB. Unknowns is equal to 6. Equations is equal to 3. Compatibility, theta A is equal to 0, delta A is equal to 0, theta B is equal to 0, delta V is equal to 0. Apart from using compatibility equations, we will use area method. SSV, theta B minus theta A is equal to AS plus AF. AS plus AF is equal to 0. Find out the value of fixed end moments and deflection at mid-span. MA, MB, SSMB are like this. Then move due to moment like this. These two AS plus AF is equal to 0. This area plus this area is equal to 0. From that we will get M is equal to PL by 8. Delta C is equal to delta C1 minus delta C2 is equal to, due to this minus due to this, we will get 1 by 192 PL cube by